Hi and welcome back to another LeetCode video. We're looking at one-dimensional dynamic programming problems. We completed 4 of them and I want to pick another one this time. So I want to pick this one, longest increasing subsequence. I think this is an interesting one that shows a more complex way of building up our previous solutions to compute the overall solutions. The solution to subproblems before we compute the final solution. So let's just have a look at it. So we have an integer array of nums, and we're supposed to return the length of the longest strictly increasing subsequence of that array. And just as a reminder, so a subsequence is any subset of numbers in the same order as in the array, but they all have to be in strictly increasing order. So here you can see in this example, we have the longest increasing subsequence is element 2, 3, 7, and 108. 101. So the subsequence does not have to have consecutive elements, but they have to be in order, in the same order as they are in the numbers array. So, well, we know it's a dynamic programming problem. So how can we actually deal with that? Let's have a quick look here at our drawing board. I'm just going to increase this so we can draw on it. And well, so one thing we want to do is understand how can we build up a solution. So typically in dynamic programming problems, what you do is you start to consider only a part of the input. So let's say we want to only consider the number 10. So what is the longest strictly increasing subsequence of an array that only contains the 10? Well, it's 10, right? So it's just length 1. What if we added to this 10 the 9? So now we are dealing with another subproblem where we consider the first 2 elements of the sequence. Well, it's still 1, right? Now, a key insight here is that if we start with a subsequence at 10 and then after 10 comes a smaller number, we know that any strictly increasing subsequence that starts at 10 cannot be longer than an increasing subsequence that starts at 9 as the next element, simply because 9 is smaller than 10. So we probably don't have to remember that we visited the 10. So let's just remember the 9. So that is now our solution to, well, the subproblem where we go over the input of 2 elements instead of just 1. Next, we encounter the number 2. The same principle applies. We don't have to remember the 9 because we know the subsequence that starts with 9 cannot be longer than the one that starts with 2. In fact, a subsequence that starts at 2 increases our chances of finding a longer one. If there are any elements here that are now between 2 and 9, then 7 would count towards a longer subsequence. So we can safely forget the 9 again. Next step is we actually run into an element that is between 9 and 2, which is 5. And I don't know why I'm drawing all the way up here. Can I select this, please? Okay. Let's just put that here. Okay. We run into 5. Well, obviously, 2 and 5 is a strictly increasing subsequence, so let's not mess with it. Let's just remember that. Next step is we're going to run into a 3. So now we have the same case again as we did before. Well, we know that the subsequence that started at 5 cannot be longer than 1 at 3. So here it's safe to forget the 5. And we're just going to remember the 2 and the 3. And our longest subsequence before had length 2 with the elements 2 and 5. And now it's still 2, but it has the elements 2 and 3. And 3 is smaller than 5. So that's a better guess or a better bet that this might be actually part of our longest increasing subsequence. Now we run into 7. Happy days. It's larger than 3, so we don't have to do anything. Then we run into 101. Again, we don't have to do anything. Now we run into 18. Well, 18 is again smaller than 101. And it's larger than 7. So we could forget about this. So the longest increasing subsequence here, they say it must contain the element 101. But what we have here now, 2, 3, 7, and 18, is just as long. So it's also a longest common increasing subsequence, isn't it? And since we only need to return the length, we arrived at the correct solution. Now you might think that just checking if the previous element is in the array is good enough. But what if we have a scenario where it's not that straightforward? So for example, if we had the sub-array, let's say, so this is our input, 4, 5, 6, 1, 2, 3, 7. Let's say this is our nums array, right? I wish I could draw with the mouse. Okay, so let's say we have this. There you go. And this is our array. Well, let's go through the motions again. So we run into the 4, we run into the 5. They're all larger, so they're strictly increasing. So we build up the solution up until 6. But now we run into the element with value 1. So what do we do? Well, 1 is smaller than 6. So do we delete the 6 and put the 1 here? No, that doesn't work. We'd also have to delete the 5. And we'd also have to delete the 4 and start again. So, and then we're losing the information that we already built up a sub-array of size, a subsequence, sorry, that has increasing elements, and that sequence had the length of 3. So if this was the end of our input, certainly we would not want to forget what the current longest subsequence is. So, well, how do we deal with that? Now, this is not going to be very obvious, but I hope it becomes clear as I go through this. We are building up the solution, and now a key point to consider is that at any point when we iterate through an array, we could run into the beginning of a longest increasing subsequence at any point. So how do we store that? Well, what we could do is we could find the element that is smaller than the 1, right? That is smaller than the 1, and place the 1 into our solution that we're building up at that position. And in fact, that's what we're going to do. So we're going to insert the 1 at the first position of our longest increasing subsequence. Now, the sequence isn't correct anymore because the 1 comes after the 5 and not the other way around. But we still have the information of what the length is of the longest increasing subsequence so far, right? And we've incorporated the information that we found an element that is smaller and or from which another subsequence could start. Now, if 1 is larger, it doesn't make sense to insert it anywhere because we know that there can't be a longer subsequence starting from that point, from anywhere. But, or if we were to insert the value, let's say the value, oh no, that's too complicated. That's, but you know, the 1, we could run into a number that we need to insert somewhere else. Just a very quick side note. So if we had the numbers, let's say 4, 6, 7, 5, and obviously the 5 fits between the 4 and the 6. I don't know if those lines helped. What we would do when we build up the solution, we would have 4, 6, 7, and then we need to deal with the 5. And well, where do we place the 5? Well, we place it where the longest common subsequence could start. So in this case, we would place it here, or we would place it 5. And then we would have the 7. So that again does not change the longest common subsequence that we found so far. But if we find another progression here of numbers after the 5, let's say 5, 6, 7, you know, we would be able to capture that 5, 5. Then we have to insert the 6 that will overwrite the 7, and then the 7. And we would know we actually have a longest common subsequence started at 4, 5, 6, 7. So this insertion is the trick of how to capture the information that a lower value occurred after the beginning of the current longest subsequence that we found. So let's continue with our example here on the left. The next step, we're going to insert 2. Well, same scenario. Where we insert the 2? Well, we insert it exactly like I've shown here. We find the position that is smaller than the 2, and we place it just beside it. So 2, 6, right. Maybe I'll move that somewhere out of the way. Cool. So now we have this situation. Now we need to deal with the 3. So same story. Well, what do? We insert the 3 at the position just to the right of the number that is smaller than 3. So we place it in here. And finally, we have to deal with the 7. Well, the 7 again is larger than 3, so we don't have to do anything. And we've computed our maximum subsequent length of 4. So that is really the trick. And you can imagine that when you build up the solution, the space that it takes is actually just the length of the longest subsequence. And the insertion, you could do the insertion with a binary search, so it would just be log n. If you want to use a brute force approach, you could just iterate over all of the numbers in the solution that you're building up. So that would be, let's say, O of k, if we assume that the length is k elements, and of course k is a maximum of, well, the maximum value for k for the longest subsequence of increasing elements would be n. And that would be in the worst case when all the elements are in sorted increasing order in the array. Yes, so just a reminder, so we have to compare if the next number is smaller than the previous one. If it is, we need to insert it in the correct position. If it's larger or larger than the previous one, we need to append it. So those are the two cases while we iterate over the entire length of the array. So that's exactly what we're going to do. So for I in range length of nums, well, now we need to check. Well, the first number, we always have to add it to our solution, right? And now in dynamic programming problems, you use a memory to build up your solution. So sometimes just call it memory. A lot of people would just call it DP. So if you look at the DP solution, if there is an array DP or a hash map or whatever, that's the memory that is used to build up the solution to the subproblems. Okay, let's just call it memory. So we're going to get the number. So the number at position I, that is the next number that we need to consider for our to build up our sequence. And in the end, we already know this, we're going to return the length of our memory. That's going to be the result. And now we have to check, I guess, if we don't have anything in our memory, we need to add the number to our memory, right? Well, the other case is if the last entry in our memory is actually smaller than the number that we're considering. Remember, that was this case where we just appended the 7 to the 3 because 3 was smaller. So if the last cell in our memory that we're building up is smaller than our number, we just append the number. We're not using equal because it has to be strictly increasing, right? So that's why it has to be smaller. Now the other case, well, we have to do the binary search, right? So, and in Python, there's a nifty function that can help you with that. And it's worth to know it so you don't have to implement binary search from scratch all the time. Well, we have to find the insertion index, right? And the insertion index, let's just call it J, is, well, we're going to use a bisect. That's a built-in function in Python. And you can pass it an array. And you can pass it in a value. In this case, we're going to pass in our value n. And it finds the leftmost position where we can insert n into our memory without invalidating the sort order. And that is exactly what we need, right? We want to find the leftmost position where we can insert the number. And then, yeah, well, we're just going to update our memory in that place, and that's it. That's really everything there is to this problem. We don't have to take care of the edge case where the list is empty, because in that case, length of nums is going to be 0. We might want to note down the runtime complexity. So n elements in our array. And depending on how long the longest subsequence is, and we said that would be k, and O of k space, where n is then nums and k is smaller or equal than n number max length of subsequence, right? You could also say O of n log n and O of n space. That's also valid. I just like to make it distinct because we are really not using, well, there are a lot of cases where we're not going to use as much memory as we have elements in numbers. So that's worth to note that this could be more efficient. It doesn't have to be, but it can be more efficient than purely linear time, space. Yeah, so let's just run this to validate that everything works as intended. So that works. And I'll submit this. And that works as well. So yes, this is one approach. Now, there's also another one. And if you don't want to use this bisect, or if you don't know this bisect trick, I guess, you know, another thing you could do is you could build up. So here the idea is that you create an array. And let me just... So you would create a memory, and you would pre-initialize it with the longest strictly increasing subsequence up until that point I, as we iterate over the numbers. And by default, you would just write the number 1 into it and length nums, because by definition, any number is a strictly increasing subsequence in the array. So we would initialize our memory with that. And then in the end, we would just return the maximum that we found. And the maximum is something that we will write in the memory, and we'll continuously update the memory, as you will see in a second. Memory. And now, since we're writing once and nuns can be empty, we need to take care of that edge case. If len nums equals 0, we're just going to return 0 as well. Now, we have a certain time, and well, we can already see that's O of n space, because we are using a memory of space n. And in terms of time, so what we're going to do here is we're also just going to iterate over all of the numbers. However, we're going to start iterating from the first number in this case. And instead of using the bisect, we are going to update all of the previous positions of the subsequences. So let me just switch back. So just to illustrate this real quick. So if we have an array of numbers, and maybe let's take this example. So if we have this as an example, well, we pre-initialize our memory, and that consists of 1, 2, 3, 4, 5, 6 entries of 1, 3, 4, 5, 6 entries of 1. Yeah, like this maybe. And now what we do is, well, we would have a pointer I that starts at index 1. So this is where we start with our pointer I. And then we iterate over all of these numbers. And then for each value of I, what we're going to do is we're going to update how many, well, if we have the value at position I, we can look at all of the values that are before it. And if the value is smaller, then we know that we can increase the counter at that position by +1, because we just validated that, oh, the number at position I is actually a continuation of the subsequence at position that was before that. So we will have a second variable j that will iterate backwards through the array, or it will iterate forward, but only until position I. And we're going to update the memory all the time. So maybe we should go through an example here. Maybe after writing the code. Maybe the code is clear enough for you to understand. I think it would be. Let's see. And now what we do is we iterate over, well, we're going to iterate over j in range up to I, but excluding I. In Python, the range is inclusive, the first, the from, and the to is exclusive. And now what we're going to do is we're going to check if the numbers in position j is smaller than numbers in position I, right? That means we can update our memory at position I, because memory at position I tells us the longest increasing subsequence up until position I. So that is going to be the maximum of the current one, as well as the one at position j, but +1, because we now need to count I as well. So this way we're going to update the maximum length of the longest strict increasing subsequence as we iterate through the elements of I. And in the end, we will have in our memory a value for the longest common subsequence. Now we have two nested loops, and the first one goes over n, and the last one goes over n in the last case. So it's still going to be O of n squared time and O of n space. So obviously it's less efficient than our previous solution, but it's much easier to understand. So if you run into a dynamic programming problem in an interview, this is actually a good solution. It's not a bad solution. And getting to the other one, I think that requires you to have seen it before. However, with this solution, you should be able to come up on your own. So let's see if this implementation works. Nums at position I. Okay, typo. Type num instead of nums. Let's fix that. Okay, and that is accepted as well. Yes, and just, I guess, instead of drawing on this board, what we can do is we can just print memory. And we can print maybe I. So we're going to see exactly how the memory changes over time. Maybe we just print to position I +1. So we only see the relevant memory cells. So let's see here in our test. So here you see, when I is 1, the length of the common subsequence is 1, because 9 is smaller than 10. So this if statement never caught. Next, we run into the 2, same case. All of the numbers are in decreasing order. But now when we run into the 5, we actually seen for the first time increasing order. So we're actually running to this if statement where we compute the maximum of the memory, which we know is 1 by default, since our initialization up here. So it's a maximum of 1 and 1 plus 1. So that's why it goes to 2, etc., etc. So it's getting increased all the time. So that's how that works. And now by looking at this, let's see other examples. Is it that we always have the maximum at the very end? So here we have 1, 2, 3. What if we don't have? Yeah, let me try another example just to see. So if we say that nums is equal to where we don't have the maximum at the end, do we still get the result in the last cell? What do you think? Pause the video. Well, we don't, right? So we still have to do the max memory to actually find the maximum element, because it's not guaranteed that the max is going to be in the last one, which would allow us to, reduce the space complexity to a smaller number or to a constant space or something like that. So yeah, that concludes this little video. another one to check off the list. And yeah, I'll see you in the next one.